Here's something that feels almost like a magic trick. On one side, a weight bouncing on a spring. On the other, an electrical circuit. No moving parts, just current sloshing back and forth. Two completely different worlds. And yet, if you write down the math, you get the very same equation, letter for letter. Let's start with the spring. A block of mass m slides back and forth. We measure its position with a single number, x0 at rest, positive to the right, negative to the left. Pull it, let go, and it oscillates. Our whole job is to find the equation that tells x what to do. Three forces are in play. The spring itself always pulls the block back toward the center. The further you stretch it, the harder it tugs. That's minus k times x. Then there's friction, dragging against the motion, always fighting the velocity. That's minus c times x prime. And finally, you might push on the block yourself with some outside force, F of t. Now Newton's second law just says mass times acceleration equals the sum of the forces. Acceleration is x double prime. Add up our three forces. Move the spring and friction terms to the left, and out pops this, mx double prime plus cx prime plus kx equals F of t. Okay, now throw all that away and look at the circuit instead. In a single loop, we wire up four things in series: a source of voltage, E of t, a resistor, R, a coil or inductor, L, and a capacitor, C, charge, Q, piles up on the capacitor, and the current is just how fast that charge is moving. Kirchhoff's voltage law says something beautifully simple: go around the loop, and all the voltage drops have to add up to the source. The resistor drops R times I, the capacitor holds Q over C, and the coil resists change in current, dropping L times the rate of change of the current. Here's the key move. The current is the rate of change of charge, Q prime, and its rate of change, in turn, is Q double prime. So rewrite everything in terms of that one variable, the charge Q, and you get LQ double prime plus RQ prime plus 1 over C times Q equals E of t. And now, watch this. Put the two equations up side by side. The spring equation, the circuit equation. Same shape, same structure. A second derivative, a first derivative, the variable itself, and a driving term on the right. They are, mathematically, the same sentence written in two languages, which means there's a dictionary between the two worlds. Mass plays the role of the coil's inductance. Both resist a change in motion. Friction lines up with resistance. Both bleed away energy. The spring stiffness matches 1 over the capacitance. The push you give matches the voltage, and position matches charge, with velocity matching the current. And here's why this actually works, and isn't just a coincidence. The method for solving the equation only ever touches those coefficients, the numbers sitting in front of each term. It doesn't know, and doesn't care, whether they came from a spring or a coil. Same coefficients in, same solution out. So, you get a genuine superpower. Solve one problem, and you've solved both. Every idea will meet later. The natural frequency it likes to ring at. Resonance, how quickly the wobble dies away. All of it crosses straight over. Prove it once on the spring, and it's already true for the circuit. And this isn't just a cute party trick, it's genuinely useful. Some things are a pain to measure on a shaking physical machine, but easy to dial in on a circuit, where you just turn a knob. So engineers would build the electrical twin of a mechanical system, and study that instead. The circuit becomes an analog computer for the machine. So the next time you watch something swing, or bounce, or ring, remember, somewhere out there is a circuit doing the exact same dance, described by the exact same equation. Different worlds, one piece of math, and that, quietly, is the whole point.